About 2 or 3 times a century, a massive star in our galaxy explodes. The star's core may survive as a neutron star or a black hole, but the rest of it rushes into space as swiftly expanding debris behind a powerful shockwave. As the supernova remnant grows, it sweeps up interstellar gas and gradually decelerates. Yet even thousands of years later, its imprint on the galaxy remains impressive. Exploding stars and their remnants have long been suspected of producing cosmic rays, some of the fastest matter in the universe. Where and how these protons, electrons, and atomic nuclei are boosted to such high speeds has been an enduring mystery. Now, observations of 2 supernova remnants by NASA's Fermi Gamma-ray Space Telescope provide new insights. Because cosmic rays carry electric charge, their direction changes as they travel through magnetic fields. By the time the particles reach us, their paths are completely scrambled. We can't trace them back to their sources. So scientists must locate their origins by indirect means, which is where Fermi comes in. The interaction of high-energy particles with light and ordinary matter can produce gamma rays, the most powerful form of light. Unlike cosmic rays, gamma rays travel to us straight from their sources. In 1949, physicist Enrico Fermi worked out how what he called magnetized clouds could accelerate cosmic rays. Later studies showed that a variant of his method, called Fermi acceleration, worked especially well in supernova remnants. Confined by a magnetic field, high-energy particles move around randomly. Sometimes they cross the shockwave. With each round trip, they gain about 1% of their original energy. After dozens to hundreds of crossings, the particle is moving near the speed of light and is finally able to escape. If the supernova remnant resides near a dense molecular cloud, some of those escaping cosmic rays may strike the gas and produce gamma rays. But electrons and protons make gamma rays in different ways. Cosmic ray electrons do so when they're deflected by passing near the nucleus of an atom. Accelerated protons may collide with an ordinary proton and produce a short-lived particle called a neutral pion. These pions quickly decay into a pair of gamma rays. At their brightest, both types of emission look very similar. Only with sensitive measurements at lower gamma ray energies can scientists determine which process is responsible. Now, Fermi observations have done just that. They conclusively show these supernova remnants are accelerating protons. When they strike protons in nearby molecular clouds, they produce pions, and ultimately, the gamma ray emission Fermi sees. NASA's Fermi has detected gamma rays from many more supernova remnants, but the jury is still out on whether accelerated protons are always responsible and what their maximum energies may be. Nevertheless, the Fermi team has taken a major step, a century after the discovery of cosmic rays, in establishing just where they arise. Something that would satisfy, but certainly not surprise, the original Fermi.